Hi, I'm Shivani Harikesh Nair, third year direct PhD student under Dr. Richard Jang at CPES in Arlington. Today I'll be giving a brief introduction into my work titled Rethinking Grid Design, a synthetic method for creating power electronics-based grids. As a quick overview, we'll start with the background and motivation for this work, and then introduce the concept of synthetic method, and dive into some details on basic cells, interconnecting these basic cells to form complex systems, and then have a comparison between synthesis and tearing methods, and finish off with some preliminary calculation and conclusion. As we move towards achieving 100% renewable grid, there is an exponential growth in the integration of distributed energy resources and power electronics interfacing that results in complexities in grid stability and uncertainties in bus data. There's a stark contrast between the future grid and today's grid in terms of decentralized bidirectional power flow versus centralized unidirectional power flow. In future grid, there is embedded intelligence through power electronics, whereas in today's grid, augmented intelligence through SCADA and IEDs. In the future grid, we have fast dynamics versus in today's grid, there is slow dynamics due to passive elements. So there is a growing need to complement or rethink traditional load flow techniques to address this evolving grid nature and architecture. And the question that we would like to ask with this research is, can we create and expand this grid of the future by interconnecting simple power electronics-based basic cells? And to convey that, let's take a look at the Virginia 500 kV transmission network on the left side. A portion of that is redrawn. And on the right side, we see that it's reconstructed using a cluster of interconnected basic cells or fundamental units. And that is precisely the idea of the synthetic method, that we can create arbitrarily complex systems by interconnecting building blocks termed basic cells using rule-based approach. So what do I mean by a basic cell? The basic cell structure is shown on the left side. It is a delta embedded with Y, which is equivalent to a closed rectangular loop. And so both these structures are graph isomorphs of each other. The definition of a basic cell is that it's an oriented graph with 4 nodes and 6 branches or internal branches shown in orange. The nodes represent buses and branches represent transmission or distribution lines of a power system network. The branches have a fixed impedance in time. That is, this impedance can change within a range of 0 to infinity as we choose. For example, infinity implies that there is no current exchange between those two nodes and hence they are disconnected. The nodes themselves are not lossy. That is, the net current injected into the nodes is equal to the net current extracted from the nodes. On the right side, we see that the basic cell has an inherently open configuration, which is represented by those external connections. The green branch corresponds to the interconnecting branch that allows for external connection to other basic cells to form a complex structure. The blue branches represent local lumped sources, loads, or energy storage. It can also imply or account for the losses in generation, etc. So why does the basic cell have this particular structure or configuration with 4 nodes and 6 branches? So some of the factors that went into consideration for us while we came up with this configuration is that the minimum number of nodes, that is 4 nodes, is the minimum number of nodes required to show graph isomorphism. It is also the minimum number of nodes for considering 3-dimensional basic cell as the building block, as it represents a tetrahedron. It is also the simplest completely meshed network. And furthermore, it's the most complete HVDC configuration that can be constructed, which is based on the Zhangwei project with some added complexity. It is also realistically in a power system network that most buses could be connected to a maximum of 3 other buses or nodes. So now that we know what a basic cell is and how its structure came about, let's look at the next step, which is how the interconnection of basic cells to form complex systems take place. So there are some rules for this interconnection, and some of the most important ones are presented as below. The first one is that the basic cells can be interconnected through 2 ways. That's through sharing of nodes or through sharing of branches. Now, the sharing of branches is a special case of sharing 2 nodes, 2 adjacent nodes. Now, let's take a look at how we can construct different grid topologies with interconnected basic cells through shared nodes. First, we have the ring network, then we have the radial network, followed by a partially meshed network, and then finally we have a completely meshed network, which can also be imagined as no longer a two-dimensional structure and a three-dimensional structure, taking advantage of the fact that a basic cell can also be considered as a three-dimensional topology. The next rule is a constraint we need to think about while we are synthesizing a new system using a cluster of basic cells, or if we are reinterpreting an existing system as a composition of these fundamental units, which is any given configuration can be realized using only the minimum number of cells required. Now, this may necessitate a system with both shared nodes and branches. As an example, let's take a system with 6 nodes, for instance. The correct way would be to use 2 basic cells, which gives us the minimum configuration, instead of using 3 basic cells to realize the same system with 6 nodes. Now, the next rule is that, as we said before, the interconnecting branch is the only link between cells. It's a zero impedance, non-coupled branch for topological clarity. As can be seen in the figure, once 2 nodes come together to form a unified node, it collapses into it. So now that we have a basic understanding of the synthetic method, let's take a look at its complementary method, which is the tearing method, or the piecewise method of solution, known as diacoptics. It was originally introduced and conceived by Gabriel Krohn in 1964 at General Electric. This is a procedure for solving large-scale system problems by tearing or decomposing. It's based on orthogonal network theory and was later extended by Happ. The concept is that we can analyze a known system with known boundaries by tearing it into n subdivisions and solving them individually. And then the solutions of these subdivisions can be combined and modified to account for the interconnections. While both methods are complementary and on face value look very similar, there are some stark contrasts. For instance, the diacoptic method or the tearing method approaches a problem in the manner of cut and solve, whereas the synthetic method aims to build and integrate. In terms of focus, the diacoptic method focuses on known static systems, which is ideal for today's grid, whereas the synthetic method focuses on dynamically growing systems, which is ideal for designing expanded grids, which is relevant with the decentralization brought about by DERs. In terms of boundary treatment, diacoptic methods view boundary variables as critical, whereas synthetic method views the boundaries as naturally emerging as the system evolves and grows. The diacoptic method additionally is highly sensitive to the decomposition strategy, since it's up to the user to determine the location of tear based on some rules. Now, this location of tear, however, affects the efficiency and accuracy immensely. So let's dive into a case where this concept can be applied and validated, which is the case where it's power flow in HVDC transmission grids. In this case, only the line resistances affect power flow, and obviously we need not account for reactive power flow, making this problem much simpler. Additionally, HVDC transmission grids have only one type of load, which is shunt loads on nodes as shown in the diagram of a 4-terminal HVDC grid. And these loads are fully controllable VSE converters. And now that allows us to control both the node voltages, or the node voltage at one node, and or the current injected into all the other nodes. This meaning that we need not use the iterative equations, as we know the node voltages and currents and not the power. And it's also fair to assume that the HVAC grids have no influence since the converters are fully controllable. So let's take a look at the high-level algorithm for the simplest case as shown, which is 2 cells, cell A and cell B, sharing one node as shown. So for each node in each cell, the current injected or extracted from that node can be written as a summation of the current due to local lumped connections and current due to interconnection, if any. So mapping that into voltage for the open configuration, we have the voltage at each node in each cell is a summation of the apparent nodal voltage due to the lumped local connections current and correction voltage, if any. So we can write this equation with the 4x4 nodal admittance matrix for each cell. So the first step would be to independently calculate the cell apparent nodal current, voltage, and current due to lumped local connections. And the second step would be to satisfy the boundary conditions due to interconnections. That is to find the correction voltage by triangular factorization and then to know the interconnecting current. And eventually, by combining them both, we can get the actual value of voltage and current for those nodes and calculate power flow. To summarize, a bottom-up synthesis framework titled Synthetic Method was presented for scalable and dynamic power system analysis, supported arbitrary network topologies. This method enables parameter reuse by isolating invariant substructures and affected by DER integration. Further, the future work includes extending this method algorithm to include purely AC networks and hybrid networks, which might include iterative calculations and make the algorithm capable of doing that. Thank you.